So I thought we'd introduce now another kind of probability that we're going to be exploring. So that kind of probability is situations that involve compound events. So I thought there were a couple good vocabulary terms to establish before we move forward and discuss some actual problems. The first one is what actually is a compound event. So a compound event is pretty simply combining two different simple situations where we want to compute a chance or a probability. So that's what I'm defining here. The next term I want to define is what it means to be mutually exclusive. So mutually exclusive events, those are events that occur when two simple events share no outcomes. So that's a situation where they're like completely separated. So that's another word choice you might use for representing mutually exclusive events. So the third kind is kind of like the polar opposite to mutually exclusive. This is much the same as independent events had their polar opposite, dependent events, and that was whether or not one event affected or changed the sample space of the second one. Here we're not really thinking about one event affecting another so much as the fact that they might overlap and share outcomes to begin with. So if they aren't mutually exclusive, if they do share outcomes, that's called inclusive. So inclusive events occur when outcomes are shared. So it's just kind of the antipolar to mutually exclusive events. Another way to describe that would be maybe that they have outcomes in common, or the best way that I like to describe this has to do with the picture we'll investigate in a second, and that is there exists, or there is, some overlap in terms of the sample space. There's a part that's overlapping one another. So my class is now going to transition to investigating some scenarios and deciding whether they're mutually exclusive or not. In other words, are they inclusive? So let's talk about a couple before we move on. Here's one. A magazine contains 13 pages. Pretty simple scenario. What if you want to choose one page from that magazine at random out of just the 13? And you're specifically interested in looking at the chance that the page number is a 3 or a 5. So that's a compound situation because we're looking at one or another thing happening, a page that we pick being a 3 or a 5. So is that a mutually exclusive situation, or is it an inclusive situation? A simple way to phrase that is, do a 3 and a 5 overlap or not? Can you pick a page, and could it possibly be both at the same time? I think pretty quickly you'll understand that no, it can't be both at the same time. A page either has a 3 on it or a 5 on it. It can't really have both. If we went all the way up to the page like 53 or 35, yes, that's possible, but I said we're just going to look at a magazine with 13 pages. So in that case, the magazine example would be mutually exclusive. Let me write that down. So there's one example. How about another example, and then we'll start looking at some math. So let's think about this. A bag contains 4 red marbles, 4 blue marbles, and 7 yellow marbles. You randomly pick a marble. Compute the probability that the marble is red or yellow. Well, I mean, if you think about it, you've got a marble. It's either going to be red, it's going to be blue, or it's going to be yellow. It didn't say that there were mixtures of colors. These marbles are what they are, and your marble is only going to be one of those. So the marble example is also mutually exclusive. No outcomes in common. Perhaps we'd better look at a situation where that's not the case. So let's think about this one. We've got a box of chocolates. There's 5 milk chocolates, 4 dark chocolates. 2 of the milk chocolates and 2 of the dark chocolates have peanuts inside. By now it's getting complex enough that it might be nice to draw some kind of a diagram. or start figuring it out. I'm just going to try to do this one orally. You randomly select and eat a chocolate. Think about the probability that it's a dark chocolate or that it has no peanuts inside. So the thing you have to ask yourself is, are some of the chocolates that satisfy both conditions? In other words, do some of them have no peanuts inside but are also dark? And I think the way that they said it, we'd have to go back, maybe a diagram would be helpful, like I said. Since they said 2 of the milk ones and 2 of the dark ones have peanuts inside, some of them have peanuts for each type, and some of them don't. So in other words, there are dark chocolates without peanuts. In other words, there's an overlap. So a little bit trickier on that one, but the chocolates example, what I'm going to say is there are chocolates, I think we could count up how many exactly, but there are chocolates with both no peanuts, which are, you know what, I'm going to put it like this, which are both no peanuts and dark. Not the greatest sentence, but you can clearly see there's outcomes in common. So that one is not mutually exclusive. In fact, it's inclusive. And you're going to have to apply the methods that we'll look at in these next examples to compute the probability. Let's look at those. All right, so now let's look at some examples of where we need to think about the concept of mutual exclusivity. So the first one is, you roll a die. Back to the basics.
What kind of die is it?
It's a regular 6-sided fair die. So A, you want to figure out the probability of rolling a 5 or rolling an odd number. So first let's write that symbolically.
5 is an odd number.
That's going to be an issue, isn't it? So the probability of 5 or odd. That's how I would write that. But remember, on your probability calculations, I'm always going to be expecting to see some kind of event description. So, in the last lesson, we were looking at mainly the probability of one event and another. And whether or not the events were independent changed how that worked. Sometimes we had to worry about a condition, and sometimes we didn't. When you're looking at the probability of one thing happening or another, that's a compound situation. So in this time, instead of dependence, you have to check, are they mutually exclusive events or not? Is there some overlap between the two possibilities or not? And Kevin immediately identified what? 5's an odd number, so is there an overlap? Yeah, in fact, how many things are there in the overlap? Just one. So let's write this up mathematically now. This one's probably pretty easy to do intuitively, but other ones won't be as easy to do like that. So here's the rule. First you figure out the probability that you roll 5, or it's going to be addition, just like and was multiplication. Add on the probability that it's an odd number. Except you guys already agreed there was a little bit of a problem here, a little bit of a catch, and that was they overlap. So we don't want to count the 5 twice, right? So here's what the numbers come out to be. You guys can help me with that too. Chance of rolling a 5 is how much? Just one outcome out of the 6 possibilities. The chance of rolling an odd is how many? There's 3 different odd numbers out of the 6 possibilities. But if I just add those up and say, okay, 4/6, 66%, I think it's too much.
That's not good.
What have I done?
Yeah, added a number that was already.
I counted the 5 how many times? Twice. I need to avoid that. So when you have events that are not mutually exclusive, the way to avoid counting twice is go probability of one thing plus the probability of the second thing and subtract the probability of both. By subtracting the probability of both, you'll avoid counting twice. You kind of like take one of the 2 times back. So probability of being both odd and 5 is of course only 1/6 chance of happening. So here we have 4/6 minus 1/6 is 3/6. So that one is 50%. Okay. Let's look at another problem. Find the probability of rolling an even or a number greater than 3. So normally I'd let you guys do this, but we're kind of running short on time today. So, symbolically, that's the probability even, or I'm just going to say greater than 3. Not the greatest notation, but it'll work. So that's going to be even plus greater than 3. And now you guys have to tell me, are there any outcomes in common? Numbers that are both even and greater than 3? So we're going to have to subtract the probability of both. So, chance of being even is 3/6. Chance of being greater than 3 is 3/6. We'd already be at 100% there, right?
Doesn't make much sense.
It doesn't make much sense. Unless you subtract the overlap. How many numbers satisfy both things? There's 2, aren't there? 4 and 6, in fact. So that's going to be 6 minus 2 is 4/6. So this one is 2/3 chance, 66%. So that's the whole idea of why you need to worry about whether events are mutually exclusive or not. If they are, if they have outcomes in common, you can't count them twice. And that's what this rule says. Add up the 2 probabilities and avoid counting them twice. That's all this is. Simple as that. I thought we'd look at 2 more problems before we quit today, though. And you should be pretty equipped to do your assignment after those. Okay, number 2, you don't want to get trapped into this one single mindset. So this one says, instead of rolling 1 die, roll 2. Find the probability of rolling at least 1 3. I think this question can be answered like so many different ways. In fact, if you look in your textbook, they'll do it the same kind of way as these other problems. I think that way is pretty darn confusing. So here's how I'm going to do it. I'm going to take us back to a diagram that we used the other day. Might as well review it anyway. How many die are we rolling? 2. So let's roll them one at a time. We're interested in looking at whether you get a 3 or something else, right? So 3 or something else. I'll say not a 3. That's the first roll. Then you roll another die. Or let's say first die. So let's say they're 2 separate ones. So then you roll the second die. That one also could be a 3 or not a 3. And see, now I have a nice picture, a tree diagram of all the different possibilities. And I'm going to be dead certain that I'm doing this correctly. So other ways to do this problem, I just think this is a great one. Also, what's another hint that this might not be the best way to do with this idea of mutual exclusivity? Do you see anything that says or? You can think of this as like an or problem and rephrase it, but then you got to work with your language muscles. It's a little confusing. Yeah, exactly. So this really is an or, but it doesn't say it. So that might make you think, maybe I should use another tool that I've learned. So let's go and look at this. We're interested in finding the probability of rolling at least 1 3. Does this count as at least 1 3? We got 2, so yep. How about this? It's 1 3. Yep. How about this? How about this? So really, we just need to worry about those 3, add them up. That'd be one way to do it. How do you figure out the chances? Attach some numbers. Chance of rolling a 3, as you guys know, 1/6. Otherwise, it's 5/6. I don't think that changes over here because these events are independent. So these are all the same thing. So to get this up here, you'd go 6 times a 6th. That'd be a 36th. Up here, you're going to go 1/6 times 5/6, which is 5/36. I think this one works out the same way. And then this one's going to be 25/36. Yeah? So now you just need to say, I've got a picture. It describes all the things I could possibly want to know. They said find the probability of rolling at least 1 3. That counts, and that counts. So you could either add these up, or you could go 100% minus that. Either way, what do you get? How many 36ths is our chance? 11. Because that counts, and that counts. Or you could go the complement and go 1 minus. You get the same answer. Put that into a percentage and you're done. Before we leave today, I wanted to do one last example. So if the bell catches us, just take it. So this one says 3,000 drivers are surveyed. 1,700 were men, 80 were colorblind, so they must have asked them about whether they're man or woman, and also about whether they're colorblind. It's an issue for drivers because whether or not you can see the red and green lights. My father-in-law has this issue. So, only 4 of those surveyed were colorblind and women. So I added the word "and" there. They want us to find the probability a driver is male or colorblind. Now, in a problem like this, you could totally do it with the rules, just like we learned. I think a picture is a nice aid, though, but let's just start it out. So probability, we want a chance that they're a man or that they're colorblind. So you could do this by the rules that we just discussed and go plus, right? And then, do you guys think that this is a situation where they're mutually exclusive or not? Are there some people that are both colorblind and males?
Yes.
Definitely. So we've got to subtract both. And you can do it like that, or you can do it with a picture. I think the picture makes this much easier, so help me with the calculator. I'm not going to draw a tree this time. This time I'm going to draw a Venn diagram. Since we agreed they overlap, I'm going to overlap them. The events are male or female and colorblind. So, I think I'm going to start with my smaller numbers. It's a good place to start. So it says only 4 were colorblind women. So does that 4 go in this part of the colorblind bubble or the part that's overlapped? Just the colorblind, because they're not men, so they don't go in the men bubble. So how many men that are colorblind are left?
76.
76. My sizes here obviously don't match, but that's okay. So if I have 76 men that were colorblind, how many were not?
1,007.
What is it? 1, 6, 2, 4? Nice. The last thing to look at before we move on and actually answer these questions and fill it out is perhaps how many people are left in our universe over here. So I think I'm going to go to my calculator for that. And specifically, I'm going to take the overall total, or 3,000, and I'll subtract the people we know fit at least one of the conditions. So I'll subtract those men that are not colorblind, I'll subtract the colorblind men, and I'll subtract the colorblind women. So this 1,296 people is neither male nor colorblind, so they're just kind of regular women that have regular eyesight. So finding that rest of the universe part in a Venn diagram is always something you should do before trying to actually answer probability questions. It's good to just have a nice complete picture so you can so you can answer any question that you're asked. So now let's go and fill in the details for our problem. So we were specifically asked about the chance of being a male or being colorblind. You could even just look at the table here. So you can see that, is this person satisfied that criteria? Are they male or colorblind? Well, they're male, so yes. Are these people male or colorblind? Well, they're both, so definitely yes. And are these people male or colorblind? Well, they're colorblind, so yes. So it's going to be those people out of the total. The way that that matches the symbolic math that we've been manipulating is just fill it in. What's the chance of being male? Chance of being male is going to be the 1,700 men out of the total. What's the chance of being colorblind? So how many colorblind people were there total? I think there were 80. And then I think we've counted quite a few people twice, so we've got to subtract out both in order to not count them twice. So the probability of being both, while in the list of data is not so obvious, in the Venn diagram is super obvious. The probability of being both is that overlapping part, or the 76 out of the total. So if you go ahead and put those in your calculator, you can get the final answer. Since they're all having a denominator of 3,000, I'm really just going to add the numerators. And you see that my final answer here is going to be 1,704 out of 3,000. Or what? 56.8%. So that's the chance of being one or the other. If you did it the other way, you'll see you get the same answer. You're going to get 1624 plus 76 plus 4, all out of the total. And that should add up to that same 1704 number. If you don't believe me, add it up. And there you go. You can see that this is also 1704 divided by 3,000. The reason that these numbers don't quite match those numbers down there is that the way the Venn diagram is set up already makes sure or ensures that you don't count things twice. This rule avoids that at the beginning and then subtracts to avoid counting twice. So two different ways to do it, one emphasizing a picture, one emphasizing symbolic math. I think the picture is probably the better way to go, and in fact you kind of needed the picture to get this part anyway. So go ahead and use a picture whenever possible. I'll see you next time.